let's say I've got some subspace V, which tends to be our favorite letter for subspaces, and it's equal to the span of two vectors in R4. Let's say that the first vector is 1, 0, 0, 1, and the second vector is 0, 1, 0, 1. That is my subspace V. And you can see that these are going to be a basis, that these are linearly independent, right? Two vectors that are linear, or a set of vectors that are linearly independent and that span a subspace are a basis for that subspace. And you can see they're linearly independent. This guy has a 1 here. There's no way that you can take some combination of this guy to somehow get a 1 there. And then this guy has a 1 here. There's no way you can get some linear combination of these zeros here to get a 1 there. So they're linearly independent. So you could also call this a basis for V. Now, given that, let's see if we can find out the transformation matrix for the projection of any arbitrary vector onto this subspace. So let's say that x, we're dealing in R4 here, right? So let's say that x is a member of R4, and I want to figure out what the projection, I want to figure out a transformation matrix for the projection onto V of x. Now, in the last video, we came up with a general way to figure this out. We said if A is a transformation matrix, if A is a matrix whose columns are the basis for the subspace. So let's say A is equal to 1, 0, 0, 1, 0, 1, 0, 1. So A is a matrix whose columns are the basis for a subspace. Then the projection of x onto V would be equal to, and this is kind of hard, the first time you look at it, it gives you a headache, but there's a certain pattern to, or a symmetry, or a way of, you could say it's A times, you're going to have something in the middle, and then you have A transpose times your vector x. And the way I remember it is, in the middle you have these two guys switched around, so then you have A transpose A, and you take the inverse of it. So, you probably won't be using this in your everyday life 5 or 10 years from now, so it's okay if you don't memorize it. But temporarily put this in your medium-term memory because it's a good thing to know, for doing these projection problems. So if we want to find the general matrix for this transformation, we just have to determine what this matrix is equal to. And that's just a bunch of matrix operations. So that's A. What is A transpose? A transpose is going to be equal to just all the rows turned to columns. So the first column becomes the first row. So it becomes 1, 0, 0, 1. Second column becomes the second row, 0, 1, 0, 1. That's what A transpose is. Now, what's A transpose A? To figure out that, I want to figure out what A transpose times A is. So let me multiply A transpose times A. So I'll rewrite A right here. 1, 0, 0, 1, 0, 1, 0, 1. This is give us some good practice on matrix products. This is going to be equal to what? Well, first of all, we have, this is a 2 by 4 matrix, and I'm multiplying it by a 4 by 2 matrix. So it's going to be a 2 by 2 matrix. So the first entry is essentially the dot product of that row with that column. So it's 1 times 1 plus 0 times 0 plus 0 times 0 plus 1 times 1. So it's just going to be 2 for that first entry right there. And then you take the dot product of this guy with this guy right here. So it's 1 times 0, which is 0, plus 0 times 1, which is 0, plus 0 times 0, which is 0, plus 1 times 1, which is 1. Now we do this guy. This guy dotted with this column right there. 0 times 1 is 0, plus 1 times 0 is 0, plus 0 times 0 is 0, plus 1 times 1 is 1. And then finally, this row dotted with this second column. Second row at second column. 0 times 0 is 0. 1 times 1 is 1. 0 times 0 is 0. 1 times 1 is 1. So we have 1 times 1 plus 1 times 1. So it's going to be 2. It's going to be equal to 2. So this right here, that right there is A transpose A. But that's not good enough. We need to figure out what the inverse of A transpose A is. This is A transpose A, but we need to figure out A transpose A inverse. So what's the inverse of this? So let me write it here. The inverse, A transpose A inverse, is going to be equal to what? It's 1 over the determinant of this guy. And what's the determinant here? It's going to be 1 over the determinant of this. The determinant is 2 times 2, which is 4, minus 1 times 1. So it's 4 minus 1, which is 3. So 1 over the determinant times this guy, where if I swap these two, so I swap the I swap the 2's. So this 2 goes here, and then this orange 2 goes over here. And then I make these 1's negative. So this becomes a minus 1, and this becomes a minus 1. We learned that this is a general solution for the inverse of a 2 by 2 matrix. I think it was 10 or 11 videos ago, but and you probably learned this in your Algebra 2 class, frankly. But there you go. We have A transpose A inverse. So we have this guy. We have this whole guy here is just this matrix. I could multiply the 1/3 into it, but I don't have to do that just yet. But let's figure out the whole matrix now. The whole A times this guy, A transpose A inverse, times A transpose. So let me write it this way. So the projection onto the subspace V of x is going to be equal to A. Is going to be equal to A 1 0 0 1 0. Let me do a little bit. Let me write it a little bit bigger like this. So 1 0 0 1 0 1 0 1 times A transpose A inverse, right? A times A transpose A inverse, which is this guy right here. And let's just put the 1/3 out front, just because that's just a scalar. So I'll put the 1/3 out front times this guy. This A transpose A inverse is 1/3 times 2 minus 1 minus 1, 2. And then I'm going to multiply it times A transpose times A transpose. And then all of that times our vector x. So A transpose is right there. A transpose is right there. It is 1 0 0 1 0 1 0 1. And then all of that's going to be times your vector x. So we still have some nice matrix products ahead of us. Let's see if we can do these. So the first one, let's just multiply these two guys. Let's multiply those two guys. I don't think there's any simple way to do it. So we have, this is a 2 by 2 matrix, and this is a 2 by 4 matrix. So when I multiply them, I'm going to end up with a 2 by 4 matrix. So let me write that 2 by 4 matrix right here. And then I can write this guy right here. 1 0 0 1 0 1 0 1. And then I have the 1/3 that was from A transpose A inverse, but I put the scaling factor out there. And all of this is equal to the projection of x onto V. So let's do this product. So this first entry is going to be 2 times 1 plus minus 1 times 0. So that is just 2. Then you're going to have 2 times 0 plus minus 1 times 1. Well, that's minus 1. Then you're going to have 2 times 0 plus minus 1 times 0. Well, that's just 0. And then you're going to have 2 times 1 plus minus 1 times 1. That's 2 minus 1. That's just 1, right? 2 times 1 plus minus 1 times 1. Fair enough. Now let's do the second row. Minus 1 times 1 plus 2 times 0. So that's just minus 1. Minus 1 times 0 plus 2 times 1. Well, that's just 2. Minus 1 times 0 plus 2 times 0. That's just 0. Minus 1 times 1 plus 2 times 1. Well, that's minus 1 plus 2. So that is 1. Almost there. And of course, we have to multiply it times x at the end. That's what the transformation is. But this right here is our transformation matrix. One more left to do. Let's hope I haven't made any careless mistakes and that I won't make any when I'm doing this product. Because this is going to be a little more complicated. Because this is a 4 by 2 times a 2 by 4, I'm going to end up with a 4 by 4 matrix. So let me give myself some breathing room here because I'm going to generate a 4 by 4 matrix right there. And so what am I going to get? So this first entry is going to be 1 times 2 plus 0 times minus 1. So it's just going to be equal to 2. The next entry, 1 times, this column times, this row times any column here is just going to be the first entry in the column, right? Because it gets zeroed out. So 1 times 2 plus 0 times minus 1 is just 2. 1 times minus 1 plus 0 times 2 is just minus 1. 1 times 0 plus 0 times 0 is 0. 1 times 1 plus 0 times 1 is just 1. Right? When you take this row and you multiply it times these columns, you literally just got your first row there. Now let's do this row times these columns. Now you got a 0 here, so you're going to have a 0 times the first entry of all of these and a 1 times the second one. So 0 times 2 plus 1 times minus 1 is minus 1. 0 times minus 1 plus 1 times 2 is 2. You're just going to get the second row here. 2, 0, 1. And that actually makes sense because if you just look at this part of the matrix, it's the 2 by 2 identity matrix. So anyway, that's a little hint why this looks very much like that. But we're just going to go through this matrix product. Now you multiply this, let me do it in a different color. You multiply this guy times each of these columns. That guy dotted with that is just going to be 0 because this guy is essentially the 0 row vector. So you're just going to get a bunch of zeros. And then finally, this last row, it's 1 times the first entry plus 1 times the second entry. So this guy is going to be 2 plus minus 1, which is 1. Minus 1 plus 2, which is 1. 0 plus 0, which is 0. And then 1 plus 1, which is 2. And all of that times x. And there you have it. This is exciting. The projection onto V of x is equal to this whole matrix times x. So this thing right here, I could multiply the 1/3 into it, but we don't have to do that. That'll just make it a little bit more messy. This thing right here is the transformation matrix. The transformation matrix. And it's as you can see, since we're transforming, remember this projection, the projection onto V, this is a linear transformation from R4 to R4. You give me some member of R4, and I'll give you another member of R4 that's in my subspace. That is the projection. So this is going to be a 4 by 4 matrix. You can see it right there. Anyway, hopefully you found that useful to actually see a tangible result. R4 is very abstract, so this would even be beyond our three-dimensional programming example. This would be, we're dealing with a more abstract data set where we're interested in finding a projection.